Turn it on. I'll just wait for a few participants to load in. Okay, so shall we start? Great. Hello and welcome everyone to the second day of the second International Symposium on Data Analytics, Risk and Technology. The symposium is hosted by the DART Lab and RBC DSI. Well, many of you might be familiar with these centers within IIT Madras. For the benefit of those who are joining us newly, I just thought I'll spend a few minutes and introduce these initiatives and centers. So the data analytics, the American Express Lab for Data Analytics, Risk and Technology is a cross-disciplinary research laboratory within IIT Madras. And its primary research focus is in three areas: risk analytics, behavioral sciences covering human behavior, and the technological platforms. The symposium is run in partnership with the RBC DSI, or the Robert Bosch Center for Data Science and AI, which was established with the purpose of achieving global prominence in the areas of data science and artificial intelligence by carrying out fundamental research and creating top quality researchers and IP which will hopefully result in significant societal changes. So the areas of fundamental research at RBC DSI covers deep learning, network analytics, learning with limited and partial data, causal modeling, and system-specific architectures and reinforcement learning, whereas the focuses on the applied side cover verticals such as manufacturing analytics, financial analytics, smart cities, and systems biology and healthcare. Before I turn it over to my colleague Babji Srinivasan, who will be your session chair for today, I just wanted to take this opportunity to welcome all the speakers. We have three eminent speakers: Professor Denny Yu from the Industrial Engineering Department at Purdue, Professor Rick Thomas from the School of Psychology at Georgia Tech, and Professor Sriram Natarajan from the University of Texas at Dallas, who's also a distinguished faculty fellow, an RBC DSI distinguished faculty fellow at IIT Madras. So with this lineup, I'm sure we're going to have some exciting and insight-filled talks, and I'm really looking forward to hearing and learning from all of you. And so without further ado, I'll turn it over to Babji.
Thank you, Nandan. Thank you, everyone. And I would like to first welcome Professor Denny Yu. Professor, to give a brief background, Professor Yu is an assistant professor of industrial engineering at Purdue University and a certified professional ergonomist. He is also an adjunct assistant professor of surgery at Indiana University School of Medicine, and also as a summer faculty fellow at the Air Force 711th Human Performance Wing. So Professor Yu's expertise is in human factors engineering with a focus on discovering objective features from sensors and health data sets for understanding human behavior and performance in complex high-stress environments. And today he'll be talking about sensing analytics for modeling behavior and enhancing performance. And with no further delay, I would request Professor Denny Yu to take the stage and provide us the lecture. Welcome, Denny Yu.
Excellent. Thank you, everybody. And thank you, Doctors Nanda Baji and Raja Gopalnath for the invitation to speak today. So I'll share my PowerPoint slides and just let me know if you can't see the correct screen. How does that look?
No.
All right. So I'll get started then. So thank you for the introduction, Baji, and I covered a lot of the, my background and some of the topics that I'll talk about today. So I'm very excited to share some of the work that our group has been doing at Purdue. And specifically, this talk will focus on the various sensing techniques, and give an overview of how we're using sensors to further some of our research interests and questions. Before I go into a deep dive into research, I just want to expand upon the background of my experiences just a little bit, quite briefly. So for my academic background, I got my bachelor's at UC Berkeley, did my PhD in University of Michigan. But then I also like to highlight some of the various industry, especially in healthcare, experiences that I've had along the way. Very, very helpful and very, each step of these experiences help inform some of the research that we're doing right now. All these experiences led me to where I am today. I'm currently an assistant professor here at Purdue, and everything I present cannot be done without all the efforts and dedication to our research team. So here's some of the students. This was taken a while back when it was, still back when we still were able to have large group meetings. Since then, we had a couple of new additions. We weren't able to have a together picture yet, but here are some of the students in our team that's definitely contributing to a lot of the research that I'll be sharing today. Before I dive into the research, just a quick couple notes, brief overview about Purdue, in case to show kind of the areas that we're in. This is the United States, and Purdue, if you aren't aware, we're right there in the middle. Ironically, it's called the Midwest, but you kind of see the region is technically to the east, so common confusion. A couple quick things about Purdue. The U.S. News have released their most recent ranking a couple weeks ago, I believe, and I think we're very known for being an innovative university and also one of the top public universities in the U.S. But that's my short plug for Purdue. Let's hop into the research. So on the research side, my group have 4 key thrust areas. The thrust areas are the 4 quadrants you see in this slide. Specifically, we're very focused and we've done a lot of work on the aching surgeon. And what that means, and a lot of this work that we've been doing or I'll be presenting today is going to be demonstrated in the surgical domain or in surgery. So the first quadrant is the work that we've been doing for the aching surgeon. We know that musculoskeletal injuries, fatigue, diminished physical performance. It's a problem across industries, be it manufacturing, construction, agriculture, but there are some unique challenges in the surgical domain. And I'll talk a lot more about that on how we are addressing or understanding these physical factors occurring in surgical work or surgical environment. The second part is that what we really aim to do, our vision, of course, is to help our surgical colleagues, our surgeons or healthcare providers perform the best they can without risk for injuring themselves or their patients. I already mentioned the physical fatigue aspects and injuries, but doing healthcare work is also very stressful cognitively. What can sensors and sensing analytics tell us about the cognitive workload, and when does that start affecting their performance? Building even beyond that, the third quadrant here is that a lot of healthcare work is done in teams. So now we're building up into a more environment systems type of approach, and how can we use sensors to determine that? Given the constraint of time, I won't be speaking too much about how we are using sensors to understand the team interactions in the healthcare work, but definitely open to any Q&As during the discussion, the post discussion, if there's any interest in this topic area. Finally, my surgeon colleagues and healthcare colleagues always tell me this, is that they're very pleased to see that we're doing good research and identifying new problems or finding new ways and techniques. But a lot of the problems, as I mentioned, are happening today already. And my colleagues in the field are saying that we need interventions now. So the third thrust of our group is always developing, assessing, implementing, and translating state-of-the-art interventions to help our surgeon colleagues to remove some of these risk factors, ergonomic risk factors right now. For example, some of the recent work that has really caught on in the industry is exoskeletons. Basically, you kind of see here a surgeon performing some simulation using it's like a backpack, but it's supporting the upper body, and it's been shown in other areas like manufacturing, agriculture, that they're actually quite helpful in reducing some of the ergonomic stresses, the physical stresses. So do they work for surgeons? Those are some of the other work that we've been doing that's ongoing. So let me give a little bit more background on the problem and why we're so focused on surgery. Over the past 20 years, there's been a rapid increase as the surgeons here in the US, a lot of surgeons publishing on or actually realizing that while performing work, they are under a lot of physical stresses that are impacting their health, their quality of life, and also their performance on how they perform the surgery. Initially, given kind of, in the past, especially the culture in healthcare here in the US, the attitude is more like, this is, I'm doing this for the patient. These are sacrifices made for the patient. But as we know from ergonomics or just industrial engineering, that workers shouldn't expect to go to work expecting to get injured or be physically taxed beyond their capabilities. So there's starting to be a lot of work from the surgical colleagues, not just us in the engineering side, highlighting that there's a problem. Performing surgeries with these new techniques, they are causing a lot of pain, and there's a strong need for interventions. What's the scope of the problem? Well, literature has been shown as if you interview surgeons, as high as 87% of them, of your surgeons will say that they've experienced musculoskeletal symptoms while performing their work in surgery. And from the ergonomics field, we know that there's some key things to look for or key risk factors that are associated with these ergonomic or musculoskeletal injuries and symptoms. And those key things are awkward postures, repetitive movement, and forceful exertions. And of course, one of the guiding hypotheses is that if we're able to measure these, understand these, and understand the dose, how much exposure to these can lead to injuries, then we're able to better design work, better monitor the workforce to reduce some of these musculoskeletal symptoms that we see among our surgeons. So feeling pain, fatigue, something we want to prevent, but there's also even greater impact given these ergonomic injuries or factors, is that studies have shown or surveyed surgeons that a decent percentage are actually retiring early. So if you kind of imagine the amount of education and resources society placed on training surgeons, having them retire early or quitting or not being able to perform surgical procedures, that's a significant chunk. A slide that I didn't show, I think I skipped it, but of course, not having surgeons perform surgery can also lead to access to life-saving surgeries, limit patient access to life-saving surgeries. Many of these surgeries are for really treatment for cancers or things that can be, fatal quite quickly without treatment. So that's another kind of very pressing concern about this population and their effect on society. So let's go back to some of the ergonomics risk factors. Here I've highlighted a very specific type of procedure, not type, but a class or a technique. And this one's a very popular technique these days that's been catching on for over the last decade, is this concept of minimally invasive technique. Basically, a traditional surgery will cut a 12-inch or a very sizable incision or cut in the body to perform the procedure. Obviously, when you have a big cut, that harms the intuition is that it harms the patient more, or you're at high risk for bad patient outcomes. This new technique, as you kind of see here, the surgeons no longer need to cut a large incision to access the patient's organs and tissues. Instead, they just need to have small holes in the patient and then use tools that you see here to perform the surgery, which has some, again, based on intuition, a lot of benefits for the patient because you're no longer having 12-inch, 6-inch incisions, you're having a couple centimeters. But obviously, you kind of see here from the engineering side, design standpoint, these tools are actually highlighting a lot of the ergonomic risk factors that I've shown in the previous slide, in that you see head twisting, back bending forward, bending to the side. A lot of the issue also you can see where the risks in that if you are operating, and these procedures can be an hour to many, many hours in length. So constant exposure to that is a key concern that likely is leading to some of the reported injuries. Now, from the engineering side, we know some of these risk factors already. We know they're getting hurt. So what is the key challenge from the engineering side and the opportunities for sensing? Well, unlike some of the traditional work ergonomics have been built upon, that's, you could imagine, assembly line. Assembly line, these are work that you could be be relatively confident in predicting what's going to happen. These have very consistent duty cycles, as in it repeats quite often. For example, every couple minutes, you will be able to finish a certain product in a workstation. The challenge in healthcare work is that the tasks are usually rarely that repetitive and predictable. Every minute, they're doing something different. So the challenge is that how can you characterize all their exposure to these risk factors when you need to really take account of the entire day where everything is dynamically changing. Here, it's simple for us in these pictures, right? We have these pictures and say, oh, hey, look, here's the ergonomic risk factors. But the work occurs throughout the entire 8 hours, and it's very difficult to do these observations and snapshots and marking various angles manually using these picture frames that I've shown here. And just a quick note, I know that a lot of our audience may not be specifically in the healthcare area, but healthcare work and this kind of the problem of having work being unpredictable or more complex, that's definitely seems to be the trend worldwide, where work is moving towards away from repetitive assembly type of work to more complex and more high skilled level work. So hopefully some of the techniques that we see in this unique population can be generalizable to some of the work conditions that we can potentially foresee in the future. So how are we tackling this key challenge? With that, I'm going to jump into some of the research. And for those research quadrants I showed, given the limited time, I'm just going to show some samples and very brief kind of ideas and some findings that we had in each of those areas to demonstrate kind of the wide utility of sensing and how it can further our understanding of these unique challenges we see in characterizing ergonomic risks, both for physical in this presentation right here, and also in a couple minutes, I'll talk about some of the other factors like the cognitive side. So just to recap, our question is, given this unique challenge in healthcare and also our need to understand, what exactly the surgeons are going through throughout their entire exposure or their entire work cycle, the research question is, can we use sensing to characterize this the exposure during complex surgical work? And more importantly, can we then take the information, and it's not trivial, can we take the information from sensing and predict fatigue or predict injuries? So we went into the operating room. These are some of the, one of the pictures here in the left is a picture of surgeons actually performing a case in our study. And then on the right, this is an illustration of another procedure that is rapidly growing, robotic surgery. So we're collecting a wide variety. The intuition of collecting a wide variety is that we want to have both, very extreme on the tail ends for our models or to construct our sensing models. So we collect the data on 12 surgeons, multiple cases. Unfortunately, there's not too many surgeons in the population. However, they do perform many, many cases. So we followed several surgeons, collected a lot of cases, both from the laparoscopic with the long tools you see on the left, and also robotic cases. We also had an opportunity to capture some exposures, some sensor measurements from the robotic cases. Here's some of the sensors that we're using. And it's basically an accelerometer called inertial measurement units. And then we also were detecting kind of muscle fatigue using surface EMG or electromyography. So for the sensing pipeline, so the IMUs or the initial measurement units, they provide us somewhat like an acceleration measure. They actually outputs quaternions. And here's the standard pipeline for how do you take that sensor measurement to extract variables that may be relevant to ergonomics, the posture measurements that I mentioned, the repetition measurements that I mentioned. So I'm not going to go too much in depth, but these are some of the typical pipelines you see for analyzing ticking accelerometer or motion-based data and extracting ergonomic risk factors. Here, the EMG are sensors that detect the muscle activity. Basically, the general overview of the sensor is that when our muscles are activated or contracting or being used, electrical activity or electrical stimulations is happening. And then these detectors, these have electrodes, these sensors have electrodes to detect that electrical activity. So what happens here for this sensor is, again, we use the traditional technique where they looked at the sensing measurements from the beginning and the end and compare it. This is the mean power frequency, and comparing it, some studies have shown that if the difference in the mean power frequency is over 8% or the MPF is over 8%, those are a key indicator that people are getting fatigued. Now, those are all things that people have done already. That's not novel, but our team is actually very interested in a novel approach in that, okay, so people have done analysis on EMG, have done analysis on accelerometers. What can we do in terms of, we have an opportunity here collecting both multimodal sensing. We have sensors for the posture, have sensors for the muscles. Can we integrate these signals? And what we did is that we created a metric called the integrated MPF, where we're able to take the posture measurements and use that information to make to compare the before and after of the MPF for a more controlled comparison. And I can go into that a little bit more detailed if those in the audience are interested in this new technique. But each of these studies that I'm showing, most of them will be published already, and I have the QR code in case you're interested in more details. So how do you get currently the gold standard or ground truth in the area to get these fatigue discomfort workload measurements or do surveys? So we did a lot of survey measurements, and some of the quick results that we show is that we basically quite match well with the literature from our study, and that we also showed about 80% of those cases that we recorded or surveyed surgeons, they are reporting that experiencing shoulder and neck stiffness and pain. One interesting metric that we use is also kind of did pain increase. So 80% happens after the surgery, but did the surgery make things worse? From that, we showed that about 39% after performing the surgery or while performing the surgery, the pain actually increased. So very very revealing in terms of the continual need for ergonomics research or engineering for the surgical work area. We also showed using traditional analysis like the posture that people that report pain, people that do not report pain, they have different postures. In this, we showed that the neck stiffness associated with static positioning in the neck. But this is the integrated metric that we developed. And you kind of see here, just using the regular MPF on your left screen, you get some good outcomes there, or at least you see some differences and between the groups of people that report fatigue or don't report fatigue. Basically, in general, on the left, you see that people that report fatigue, they have higher MPF, higher difference in MPF, meaning that if you recall from the previous slide, If you have an 8% or more, that is likely indicated fatigue. So our sensor measurements corresponds well with also what the people self-report. The second plot in this graph is the integrated MPF, and we show that it's actually much more specific in identifying fatigue. You can kind of see that the reduction in MPF is much higher, showing that if we factor in the posture or control for some of the posture using our accelerometers in our integrated method, we're actually able to identify fatigue more relevantly. So you can kind of see here also the difference for people reporting fatigue and no fatigue increase. Just a couple takeaways in this area is that from this just brief overview of this work is that musculoskeletal pain continues to exist in surgery. We demonstrated that wearable sensings can monitor these work exposures even with all the complexity and restrictions in the operating room while maintaining the performance and safety for the surgeons and also for the patients. We showed one of our key contribution is that multimodal sensing enhances our ability to predict fatigue in these complex work exposures. Quickly moving, I want to give a highlight on some of the challenges or limitations we saw in the previous study and some of the work that we're doing right now in more of a fundamental level. The challenge, of course, is sensors sensing. They're great in that they're getting more better power, more information, more data. However, the problem is wearable sensors is still quite cumbersome. So what can we do in terms of analytics for using computer vision? Because computer vision, you no longer have to wear sensors. The key thing is that we're focusing on computer vision for measuring force. People have used computer vision for measuring a lot of things in human behavior and activity, but force is a key factor in ergonomics, and we're not really able to measure that well. From what we did previously, this is kind of an example that we sourced illustration. Our previous study used these sensors to attach on the muscle to detect the muscle activity. Gave us very useful information, but again, quite cumbersome for the user, and you can't expect them to be able to do this every day. Other ways of measuring force, you could ask the person like we did on our surveys. You can use digital human models. You can just kind of find an expert ergonomist to make observation. But one of the interesting things that when we were, of course, we were also making these observations and try to predict based on experts how much force they're using, because more force used increases your risk for injuries and fatigue. One of the things we use is this pretty well validated tool, the hand activity level. And it focuses on repetition, but they also the second part it focuses on is force. And what's interesting here is that know what the experts are looking at or trying to look for when they're trying to analyze force. They're looking for relaxed effort, definite effort, change facial expression, start movement of the trunk and shoulders. So these are very observable cues, and the question is, can non-contact sensing, computer vision, leverage these cues that experts use to detect and measure force automatically? So to tackle this, we actually conducted a study. This is more on a very controlled lab setting, but I just wanted to show this study because it really highlights potential future in the use of computer vision to potentially supplement or enhance data sets from sensing. And what we did is, you can see in this environment, we had a participant, very standard posture, sitting down, holding on to a little grip device. And that grip device measures the amount of force that a person is able to grip. And you also kind of see, we also have a camera right in front of the person. And what we were doing in this study was that we asked the person to grip the device at various levels, high, low, medium, and medium levels of force. And then we were recording the videos. And we use various video computer vision algorithms like deep face to detect various landmarks in the face. We also did some supplemented with some PPG. The PPG is heart rate. It measures kind of the kind of blood flow. The reason why we use PPG is that there has been papers published using computer vision to detect heart rate. We were not able to replicate their work, so instead we had to use a more physical device, but the technology apparently does exist for detecting heart rate just using video cameras. But anyways, we conducted this experiment, had various participants, 18 participants, perform different levels of grip force, and then did the recordings. We extracted their information from the videos, and we started training our machine learning models. And we did a couple experiments with the data sets. We tried to determine first which is the best classifier. Then we try to determine, can the computer vision by itself determine when they're doing high force or low force. The second experiment is 3 levels. Can the computer vision determine high force, medium force, or no force? For the 2 level, we got pretty decent accuracy, 96%. 3 level, much lower, 87%. But then we also had some comments from reviewers of the studies that, well, what about people just doing not grip thing, but their face is moving? So we added some robustness tests in introducing some noise, having people just talk without doing any forceful exertion, and you can see our results there. So in general, the prediction of the two class, pretty robust, and there's some promise for this technique. I do want to now hop gear. That gives you some of the overview of what we're doing on the physical side, but I know that we also have audiences that are interested in more potentially what these sensors can tackle in the even more complex challenge of the cognitive space. So I already showed this slide, but something that I didn't show is that in addition to all this physical effort or physical fatigue and injuries, there's also, you could kind of see here some of the data on the cognitive side. How mentally demanding or cognitively demanding are these surgical procedures? Luckily, a lot of the surgical team, the different colors of the bar represents different roles. You have the anesthesiologist, you have the nurses, you have the resident, the surgeons. Luckily, a lot of procedures are not that mentally demanding. From 0 to 100, a bulk of them are below kind of the median or the middle of 50. But you can also see that there's a lot of people reporting that some procedures are actually very, very mentally stressed and cognitively loaded. And that's kind of that dotted line. Some papers have shown that, potentially that's a good threshold for start seeing decrements in performance, which is critical here because the work that they're doing are directly affecting patient. Building upon this, in the U.S., they have the Joint Commission, and the Joint Commission reviews sentinel events, things like, very, very catastrophic or not expected outcomes in healthcare. In surgeries, for example, having the wrong operation, getting the wrong side operated, leaving things inside the patient. And some of the things that you can notice here is that on top of the list, human factors is one of the key things they notice as a root cause for these bad outcomes. And then just, a lot more studies showing that individual cognitive factors, channeled attention, are some of the things that are contributing to these never events or events in surgery that should never happen to a patient. So how do you measure cognitive workload? A lot of techniques and papers have been published. There's several approaches in general, questionnaires, using experts, using secondary psychology tasks, or using sensors. Here, we kind of show briefly how we develop our system to measure cognitive load, or trained our system to measure cognitive load. We focus here on robotic surgery. The motivation for using robotic surgery is it's a relatively new or growing in popularity, but instead of performing surgery as they are trained to do, surgeons are now performing surgery using the robot. And this transition, this change is likely, the intuition is that it's highly disruptive and will increase their cognitive workload. So we did this study on surgical residents. They performed simulation tasks as we saw in this slide right here. And while performing these tasks, they wore sensors. Specifically, the first data set findings focus on these eye tracking sensors. So all our surgeons, you can kind of see while performing these surgical simulation tasks, they were wearing our sensors. One of the sensors you see wearing is this eye tracker, the Tobii eye tracker. From this eye tracking sensor, I know that I think there might be already material on this in the symposium or online. We extracted features using these eye tracking that's relatively common in the literature for eye tracking techniques. So let's go straight to the results. And we showed, or we try to demonstrate sensing and predicting workload in 3 different methods. First, we showed can sensing predict workload changes due to the task. Each of those simulation tasks have different difficulty levels. Think of it as like a video game, a hard level, easy level, medium level. And you can kind of see here that this eye tracking measures, 2 different measures were able to relatively reliably distinguish difficulty levels of the game or each individual task. The pupil diameter typically showed increases as the difficulty level increased. And then we also see gauge entropy, which I didn't show here, but I'll show in the next slide. The next way of showing whether we can experiment and use sensors to predict workload is comparing it with self-reported. We have every participant surveyed on what their cognitive load is based on their validated surveys. And we showed that the sensors metric for eye tracking, gaze entropy, were actually the more predictive, or actually significantly associated with their self-reported workload. The third way of showing or using sensors to predict workload is using a classification model, in that we took features from the sensors and some of the physical features like gender and experience and integrated into a naive-based classification model to detect between high and low workload. And we show here that the detection accuracy using these features in eye tracking, relatively accurate, about 85% accuracy. Now, the last slide, or kind of a small overview of a study, is that I showed eye tracking previously, but we also did another study leveraging what we showed in the first study on multimodal sensing. So we know that cognitive and mental workload is very, very complex, and sensor data, especially the sensors that we have or demonstrated, even eye tracking, are quite noisy. So can we leverage multimodal sensing to even improve our ability to detect workload? We conducted a separate study, but similar methodology, where we had residents perform surgical skills tasks on the robot, different difficulty levels, different types, at different stressors, have them self-reported, and then while at the same time, were various sensors. We have brain activity sensors, EEG, heart rate monitor, galvanic skin responses, EMG, like we showed in previous, the first study, and also IMU, the accelerometer. And given this, we demonstrated that using kind of a multimodal, we extracted features from these sensors and then experimented with different ways of using the data, and then various models and classification models to take features and predict cognitive workload. Comparing again high and low cognitive workload, we showed in this paper that we can, by using multimodal sensing, we could perform, do classification and predict workload to about 83% accuracy. So I am running a little bit over, so I apologize for that, but I can't end the presentation without thanking the team members and the faculty that are all, and collaborators that are all involved in this project. All the work that I've shown here is a massive team effort and undertaking, both from the faculty side. We have our surgeon colleagues, colleagues in machine learning, colleagues in robotics. We also have our students, students in medicine, students in engineering. We have students in, again, computer science or machine learning. So love to definitely need to thank them for all their contributions to the work that I present today, and also, of course, some of the funding sponsors that contributed in parts funding to support this type of work. With that, I would love to hand it back to Baji if there's any questions that I could help address or answer now, or maybe later throughout the symposium. Again, thank you, everybody, and thank you, Drs. Sarah and Vasan, for the invitation to speak at today's symposium, and thanks for the audience for attending this talk.
Thank you so much, Professor Yu. It was a wonderful talk on sensing analytics for modeling human behavior. So, before I ask questions from the the question and answer panel, I have a few questions. So one of them is when you talked about this multi-model sensing. So each of them, I believe the sensors collected different frequencies, and therefore they also have at time scale issues. and the correlation between them is also at different time scales, and it may not be always uniform. The correlations will also break down and catch up. So how did you handle, and how did you come up with a combined metric, or are you working in individual metrics?
Excellent. So excellent question. So I say our work really right now is just scratching the surface of what sensors can do. So a lot of the things that we're doing, we're actually summarizing the continuous measurements into various windows. So we're taking statistical descriptors to summarize, for example, 5-second, 10-second window and move that window across the data. What we are currently trying to do and try to start doing with some of the computer vision is that take the continuous time series. That gets much more computationally complex, but that we believe is potentially can enhance our ability to even better use the data than just summarizing them with the various time windows that we've done currently.
Okay.
But that's definitely something that is a key area of future work that must be explored, because you have such rich data. There's no reason to kind of really downsample basically what the data is giving us.
Thank you. And the other question I had regarding team dynamics, when you talked about team analytics, so you were saying that although you didn't present here, so did you look at the team dynamics and then the cognitive aspects of a team? And,
Yeah.
okay,
Excellent. So just to give a highlight on what we're doing with the team dynamics, you can kind of see the kind of the vision and pathway of kind of our research group is that we are building, these are the different building blocks that are not separate but building upon each other. So the sensors that we're using, I showed that the surgical team, you have multiple roles there, and very skilled interaction between team members, because you can't perform the surgery by yourself. So what we did is that we then applied, currently we have sensors on all the team members, and then figuring out the interaction. So we have interaction metrics that is actually ongoing work. We published some, but we have a lot more in the pipeline. Is that how do you quantify interaction between team members? You can have proximity, you could have communication. So now we're talking about natural language processing or how to process audio. And something that we've been doing is doing also traditional coding. So communication field have a lot of techniques on coding the dialogue, non-verbal interaction. So a lot of opportunities, and that's why you kind of see all the sensors that we have. We scaling up to the team level, and also of course have video cameras, and hoping that by building some work on the computer vision side, we're able to also enhance and remove some of the manual work. So automation is also another key thing that I'm looking forward to in the future of sensing and computer vision.
Yes. Thank you. Because I think you are doing both video, audio analytics, and all of the other put together, if I understand, right?
Excellent. And I've read some of your team's work, and I think there's a lot of, there's a lot of efforts going on internationally that I think we'll see a lot of progress in this field in the very near future.
Yeah. So I'll take a few questions, one or two questions in the interest of time from the audience, and then the rest of the questions I think you can answer it over the question and answer window. So one of the questions is, from Gayatri, is haptic technology being used in this research? If yes, would you elaborate why and how?
Excellent. So one of the things that I unfortunately didn't talk too much about is various interventions, because currently all the work that I presented today is just really advancing our ability and the science on understanding what the people are experiencing and what their exposure is. One of the key things is that when we're developing interventions, whether it's AR, whether it's providing exoskeletons, tactile feedback is some of the things that is a modality for transmitting information. So currently we have not have any work done in the tactile or haptics area. We know I know some robotic colleagues that are doing a lot of work with focusing on providing some haptics for the robot, because in the robot, unlike physical touch, it's not going to be able to provide you that information, and that's a significant concern for safety. So colleagues are working on that. I'm hoping that in the very near future, we could start merging our expertise is once we develop better models of understanding the behavior of humans, start using haptics and integration of haptics to better enhance their performance while performing these tasks.
I'd say one last question from the audience. There are multiple questions, but I will pick up one more. So one question from Martina. She was asking, has the current pandemic influenced the studies, meaning owing to the stress that the healthcare has faced? So what is your take on how it has impacted the stress levels and any studies on that?
Can you repeat the first part of that question?
Yeah, so the question is, has the current pandemic influenced the studies or analysis, specifically owing to the stress that the healthcare has faced? So any studies or things that has been done the pandemic times?
Oh, excellent, excellent. You guys are really just predicting a lot of the work that we have in the pipeline. So yes, pandemic has affected things, everything global, worldwide, and healthcare is especially healthcare. For what we've done is, so a lot of research has focused on the effect of pandemic and the additional stresses that it can create. Unfortunately for us, we weren't able to measure it quantitatively with our sensors given restrictions with doing in-person study, but we are doing some other work in terms of, so going back to Baji's question about teams. One of the things about teams is a construct called decision making, right? Teams are leveraging information together to make decisions. And we did some studies. This is more of a quality study that we published, looking at how pandemic changed how team care providers make medical decisions. So in summary, that work shows that, all right, when you're thrust into this brand new situation, how does it affect your ability to make accurate decisions or interact with your team? That work we did is with nursing. So we focus on nurses and their ability to care for patients, and how did the pandemic, the additional stressors, how did that limits the amount of information they could get, or how did it open up new sources of information that they can get and gather to make decisions? So very excellent question. And that's definitely some of the area that we are hoping to also advance. It's something that we have in the pipeline. So thanks for that question.
Thank you, Professor. And then there are some other questions which you could answer in the chat. In the interest of time, I once again thank you for the wonderful talk on the sensing analytics and your answers to the questions as well. And yeah.
Excellent. Well, thank you again, and thank you all for the questions. I look forward to the Q&A session at the end of the symposium.
Thank you.